Hi guys, here we are looking at a little weird experiment with our Shamus remake using the retro character map video display driver, which is just a library of functions that kind of create a simulated VIC-20, something like that. Let's take a look at what we have today. I think since we first looked at it, we've improved the sprite rendering a bit, so sprites can move along the x-axis and along the y. They couldn't initially. And now we have character allocation as well, which means that each frame we need to reset what characters are used and what characters are not. In this very simple frame, we have one character that we are using that is protected. That's character 0, because that's reused across the whole screen. And every other character from 1 to 255 is available to be rendered onto. Let's take a look at it anyway. Looks much the same as it did before at this point. So I'm controlling that little guy there, and we've got a bunch of other ones. The top right hand corner shows us how many characters are available to render onto. If we exceed that, there we go. Then we get graphical glitches because we've got nothing more to draw onto. But we can get a fair few characters on screen moving around without hitting that limit. So we could probably have, I don't know, maybe 50 or so tiles for our environment, which for Shamus is pretty acceptable. And the rest can be just our character sprites. So we haven't got any clipping in this. It's still I've just sort of been updating the rendering to get it to work yesterday. Clipping will. I don't think the original game had clipping. Here with our coordinate, as it becomes negative, we should nicely clip to that side there and not reappear on the other side, but it does for now. Okay, let's get rid of those color map rendering stuff. Where is that stuff? I think it's in the render sprite routine, which looks like a bit of a nightmare, and I guess it kind of is a bit of a nightmare. So a sprite is made up of 8x8 pixel blocks. They're two color. We have 1 byte represents 8 pixels. So each bit represents a set bit represents a foreground color, and a clear bit is a background color. So you can't have multiple colors within the same sprite, and they can't share each other or share between different sprites. You would have seen this effect on, I think the Spectrum has a similar kind of memory map. The VIC-20 and 64 have similar modes. I'm not emulating those modes, we're just kind of making something that's sort of roughly around that. Sorry, I'm just looking for where the backdrop color is. I think it's in that function there. Yeah, there it is. This is just used to give me an indication about what it's rendering on, what blocks it's rendering onto. You can get rid of that. So it look more like some sprites, you know. So we can have a fair few of them on screen without it dying, which is pretty cool because that's about what you need. What's way beyond what you need for a VIC-20 game. I think the characters in Shamus were actually probably one tile in size, except for the main monster, which was the Shamus. I'd have to see it again. I actually can't remember. Probably should have done that research before I started. But there you go. We've got our sprites move. a little controller code is moving the sprites with a floating point. So we can have partial, or we're not moving it pixel by pixel every time. So they can move at different rates, is what I'm saying. Little objects here. We've got our position, our speed, or direction, you might want to think of it as, and a little driver function down here to update those objects on screen. We've got a bit of a randomizer. So if you press enter, it can generate some objects, or it'll automatically generate objects if this statement here is true. So if it chooses a random number and it's bigger than 990, then we proceed down to here. We're doing a random between 0 and 5, so you'll either get one object or up to 5. We'll make it a bit less. And we're just adding a new object to our list, giving it a position within the screen constraints of the physical screen resolution, which is much smaller than our actual resolution. Because our screen is 22 characters wide, our actual resolution is whatever this is by 8. So 22 by 8. Not very high, is it? We're choosing a speed. We're using a loop there just to make sure that its speed it's not 0, 0. We don't want the object to sitting there forever. We want it to move off screen. The processing loop is as you expect. We grab its position and we add its speed. Do a bit of a clip on the x-axis. If it's outside of the bounds, we kill the object and skip over the rest of the code. If it's outside on the y bounds, we do the same thing. If not, we render it. This value here is actually where our sprite, a little spaceship, is actually located inside our memory of our simulation, which we load into memory up front. Anyway, so once we've drawn the thing, we reposition it. We store its new position in our structure, and we just keep processing our little objects. So, as you have seen a million times before, the same kind of processing loop. Our play is just a bit of a mock-up here as well. Nice car going past there. So when we do a CLS, we're filling the character screen and the color map. And this is character 0. It's the character we want to fill the background with. And this means the background color is color 0. Let's change that. We'll change it to, I don't know, color 5. We'll see what we get. I've got a very horrible looking yellow. The color's just randomly generated, by the way. Yeah. So all those tiles, every tile has the same background color. We can change the background color per 8x8 tile or character. We can change the foreground color of the tile as well. Change the foreground color to 3, so it won't be white this time. It'll be, there you go, it's green. They all appear green because every tile on screen has the same color characteristics. There you go. It kind of produces something that looks like an old Vic-20 game. This stuff here was added the other day. We have a heap of characters. We'll check out this little function, and we have a heap that we use to tag different characters that are actually we're going to be using, and characters that we are allowed to modify. So we have 2 arrays. This is the protected characters. That's, in other words, if we have characters on screen that are repeated more than once, we cannot modify their graphics, because doing that would mean that all the modifications are shown up in the other characters. We can just force it to show you that, actually. We just go Add to character heap, 0 from here. Now, yep, it's not happy with that. So we're rendering into a character that it considers to be protected. All right, so with this array here there are 0 to 255 character possibilities. That's 8-bit. They're either protected or they're not. So they're either set or they're not. They're either 1 or 0. If a character is set to 0, that means it's allowed to be rendered over and dynamically rendered too. If it's set to 1, it's not allowed to be. All the characters that are allowed to be rendered over, we put them in this little heap. Where is that? Okay, so this is our clear heap function. We're setting all characters to protected by default, so they're all not allowed to be drawn over. And then we're telling it that we want to draw over, or we're asking it to allow us to draw over certain characters within the stream. So we can do this. We can add one character individually, or we can do it by groups. I just figured by a group is probably easier most of the time. So what this function does, it just runs through and adds all of the characters or the, you might think of as blocks or tiles or whatever language that you feel comfortable with. Adds all those things to our little heap. And then as we're rendering and we need a new tile to render onto, we just poll the heap, get the top value off the heap, and just drop the count. And that's down here somewhere. So this is our pop heap. We ask for the number of tiles, the number of tiles in the heap, -1. Make sure it hasn't underflowed. If it hasn't underflowed, we get the tile, we set the new count, and return the character. And a function to return the heap size so we can see it on screen. Now, when we use this stuff in our sprite rendering, sorry, I'm jumping around a little bit here. So, okay, it's our sprite render here. We're drawing each 8x8 chunk of the character onto different target characters. And so what it does now is that I've kind of wrapped up some of the garbage into a function that we can just ignore. So we've got a very simple inner loop now. It's ugly, but it does what it sets out to do. So what we're doing when we're drawing our sprite, we work out what tile it's over, the amount of shift required, the amount of bit shifting required. Then here we work out, is that character or tile that's being drawn over, do we actually need, can we draw over that tile, or do we have to make a copy of that before we can? So we're getting pointers to where the actual graphics are in our system memory. We're getting a pointer to where the screen memory or character map is. We're asking and reading the character from this location on the screen. We're asking it, is this a protected character? If it is, then we have to do something with it. We have to ask for a freely available character that I can render over. I have to write this back to the screen. So when the screen is drawn, it's changed the character map to point at our newly drawn graphic and not the original graphic. And then here we make a copy of the actual graphics that was in that old character. So we get the source, address of the character, the destination, and just copy it byte by byte. At the end, we set this character to new character, and that's it. Or here we'll return the actual pointer where this thing is in memory. Bit of a yawn fest, I know, but I know it's kind of a very weird thing to do, and why would you do this? Well, it's something that will help people appreciate just how incredibly awkward it was to make games on old 8-bit systems. These days we see a lot of people talking about making retro games, my game's a retro 8-bit game or whatever. And you go, no, that's not even close to what a retro 8-bit game was like. Because those things had real limitations. And I think our other function there just changed it back to what it was. So the sprites are in white, and these will be... If I turn the background to white, you won't see anything. Doesn't matter what happens. The two colours are the same. So I could actually optimize that out in the renderer and just get it to... If it detects the block is... the background and foreground colours are the same colour, then it can just draw a square block for that tile. Yeah. I don't know why you want to, but you could do that. Vic-20 Space Invaders. But it's all about actually having a real understanding of how these kind of systems work and wrapping your head around some weird limitations. And when people make modern remakes, they don't have those limitations. They think, well, if I just set the palette to... If I reduce my colours and make the pixels blocky, that means it's an 8-bit representation. It kind of does, 8-bit means different things to different people. So 8-bit graphics in terms of, old PC games or DOS games means you've got 8-bit or a palette of 256 colours. When I tend to think of it, I tend to think of the limitations that pop up in VIC-20, the 64, the Spectrum, the Amstrad, all these old systems that require a lot of painful effort to actually get them to do something. Anyway, guys, that'll have to do us. Just wanted doing these things on the run, messing around. Hope you're enjoying 2019. I'm sort of sitting here in the couch, unable to move much, laid up, injured. Which is one reason I'm kind of doing this at the moment as well. It's just something I can do where I don't have to be in the office sitting down. Anyway, thanks for watching, and we'll catch you next time. We might try and get some map representation going or something like that. See how we go.